Have you ever just stopped and looked at your hand or the desk you're sitting at and asked, why is this here? Why does it all hold together? It feels like the most basic question in the world, but it turns out to be one of the most profound puzzles in all of physics.
Because really, when you get right down to the nitty-gritty, the simple fact that the world around us is solid and stable is a total mystery. And today, we're going to dig into why the very existence of matter is, well, it's nothing short of a quantum miracle.
And here's the real kicker, the thing that gets this whole story started. Before we figured out quantum mechanics, our best theories, the laws of classical physics, flat out predicted that stable matter was impossible. Everything should have just collapsed the instant it came into being. So that brings us to what we can call the atomic paradox. The fact that you and I are even here to talk about this is proof positive that our old understanding of the universe had a massive, gaping hole in it.
Yeah, and we're not talking about a minor little rounding error here. As this quote puts it so well, the simple, observable fact that atoms are stable things was a giant, flashing red light for physicists. It screamed that a huge, fundamental piece of the puzzle was missing.
Okay, so to really appreciate just how brilliant the solution is, we have to spend a minute with the problem. Let's take a look at that old classical model of the atom and see exactly why it was doomed to fail so spectacularly. The classical model feels really intuitive, right? It pictures this tiny little electron, like a planet, zipping around a central nucleus, like the sun. It's simple, it's elegant, and it is completely, catastrophically wrong. So here's the fatal chain reaction. First, basic physics. Anything moving in a circle is technically accelerating. That's just a fact. Second, one of the core rules of electricity and magnetism says that when a charged particle accelerates, it has to give off energy as light. Third, as our little electron radiates away all its energy, it loses its momentum and can't fight the nucleus's pull anymore, so it starts to spiral inwards. And fourth, poof, game over. The atom collapses. And this isn't some slow decay we're talking about. The math predicted this entire collapse would happen in about 10 trillionths of a second. That's basically instant. If classical physics was the whole story, our universe would just be a boring, featureless soup of radiation. No stars, no planets, no us. But, just look around. That's obviously not what happened. And the hero of our story, the completely new set of rules that saves matter from destroying itself, is quantum mechanics. This is where reality gets really, really weird. And in doing so, it becomes stable. The first part of the rescue is a total shift in how we even picture an electron. It's not a tiny little ball zipping along a path. Instead, a quantum electron is a wave function. Think of it as a smeared-out cloud of possibility. It doesn't have one precise location, just areas where it's more or less likely to be found. And that single change, well, it changes everything. Okay, part 2 of the rescue mission is this idea of a ground state. So, unlike a planet that can orbit at pretty much any distance, an electron is stuck on specific energy levels, like rungs on a ladder. And here is the crucial bit. There's a bottom rung. Once an electron gets to that lowest energy level, it physically cannot lose any more energy. There's just nowhere lower to go. So that death spiral we talked about, it's literally impossible. And for the final nail in the coffin of the classical catastrophe, we have the Heisenberg uncertainty principle. And this is so important. It's not just a limit on how well we can measure things. It is a fundamental, built-in rule of the universe, and it provides the ultimate defense against atomic collapse. Let's walk through how this works, because it's pretty wild. For an electron to fall into the nucleus, its position would have to become super, super precise, right? Well, the uncertainty principle says, not so fast. The more you pin down an electron's position, the more its momentum goes absolutely haywire. So trying to squeeze it into the tiny nucleus gives it this enormous, uncontrollable burst of energy. It creates a kind of quantum pressure that pushes back. Trying to force an electron into the nucleus is like trying to squeeze a spring that gets infinitely strong the more you push it. It just won't go.
So let's just lay it all out. It's a complete 180. Where classical physics predicted an inevitable collapse, quantum mechanics forbids it. Instead of a point particle that can have any energy, we get a stable wave function with fixed energy levels. And because of that, we get atoms with a defined stable size. It's a total game changer.
Okay, so we've solved why atoms don't collapse. That's a huge step. But what about, well, everything else? It turns out the very same weird quantum rules that save the atom are also what allow them to link up and build the entire world of chemistry. It all comes back to that same principle of finding the lowest possible energy state. Just like an electron wants to be in its ground state, whole atoms can find arrangements with other atoms that have a lower total energy than they would if they were just floating around on their own. In physics, lower energy almost always means more stability. So how do they do it? Well, those electron probability clouds, their wave functions, from different atoms can actually overlap. When that happens, the electrons are no longer stuck to just one nucleus. They can spread out and be shared between atoms in something called a molecular orbital. And that sharing arrangement, it's a lower energy setup. That's what a chemical bond is. It's not glue, it's a more stable, shared quantum state. So let's zoom out and put it all together. The existence of atoms, of molecules, of you and me, none of it is an accident. It's all a direct consequence of the fact that our universe runs on a quantum operating system. And this is such a profound idea to sit with. Our stable, predictable world isn't a given. It could have been completely different. It exists because the universe follows a very specific instruction manual, one that has quantum mechanics hard-coded into it and all the fundamental constants tuned just right to make it all work. So here's the ultimate recipe for making stuff. First, you need the strong nuclear force to glue the nucleus together. Then you need electromagnetism to pull in the electrons. Then you need the whole quantum toolkit, quantization and uncertainty, to stop the whole thing from imploding. And finally, you need another rule, the Pauli exclusion principle, which basically says electrons can't all pile into the same state. That's what forces them into distinct shells, creating the periodic table and all of chemistry as we know it. And that really is the mind-bending takeaway from all of this. The solidity of the ground beneath your feet, the chair you're on. It's all an emergent property of these strange, fuzzy, wave-like probabilities and fundamental cosmic uncertainty. Matter is what happens when quantum rules tell energy how to arrange itself into stable patterns. Which leaves us with one last fascinating question to ponder. We understand the recipe that made our universe. But what if those fundamental constants were just a tiny bit different? Would the universe be empty? Or could there be other kinds of stable structures out there built on a foundation of physics that we can't even begin to imagine? Something to think about.